Welcome to this explainer. Today, we're diving deep into the hidden engine that actually powers modern software development. We are talking about the interpreter design pattern, specifically how we build it in Go. If you want to understand how the most powerful systems in the world actually process the commands you give them, you're in exactly the right place.
Let's kick things off with a scenario you know well. You write select star from users where age greater than 25. It's second nature, right? But have you ever stopped to ask who actually executes that? Or more accurately, what executes it? It's not magic. There's no tiny database goblin reading your queries. There is a specific piece of software designed to read that exact string of text, figure out what it means, and then run the underlying logic.
And it's not just SQL. Regular expressions, Go templates, protocol buffers, every single one of these relies on the exact same underlying mechanism. Honestly, you've been using this pattern your entire career without even realizing it. Whenever an operation is just too repetitive or way too complex to express directly in Go code, we create a language for it. And to make that language work, we build an interpreter.
To wrap your head around this, think of the grammar of your language, whether that's SQL or regex, as sheet music. Sheet music is literally just symbols on a page, right? It doesn't make a sound all by itself. The interpreter is the musician. It is the execution engine that reads those symbols and translates them into actual tangible actions.
Let's make this concrete. Imagine your team is building a fraud detection system. Your fraud analysts, who, let's be real, are definitely not Go programmers, need to write detection rules on the fly. So you design a domain-specific language, or DSL, for them. Something like amount greater than 10,000 and country not equal to in and attempts 3. They write the business rule, but you build the interpreter that reads, parses, and executes that exact logic.
Section 1, the engine room, reverse Polish notation.
So how do we actually build this engine? Well, we use a stack. We're going to start with the absolute fastest, simplest approach using reverse Polish notation, or RPN. RPN is super clever because it completely eliminates the need for parentheses. The order of operations is just inherently built right into the text. Let's trace the expression 3, 4, sum 2, sub kinetically. Imagine a literal stack of blocks on your desk. Step 1, we read a number, 3. We push it onto the stack. We read 4, push it on the stack. Step 2, we hit an operator, sum. This operator pops the last two values off the stack, the 4 and the 3, adds them together, and then pushes the result, 7, back onto the stack. Step 3, we read 2, push it. Step 4, we read sub for subtract. It pops the 2, pops the 7, subtracts them, and pushes our final answer, 5. It is incredibly efficient.
Now, if you're writing this in Go, managing that stack requires a very specific technique. P equals at P slice length minus 1. This is totally idiomatic Go for popping a value off a stack using a slice pointer. Basically, we dereference the pointer P to get the actual slice array, we take a subslice that deliberately excludes the very last element, and then we write that modified slice right back through the pointer. It's an in-place slice mutation, and it keeps our stack blazing fast and memory efficient.
The really crucial point here is how we handle those operators, like sum or sub. Instead of writing some massive, ugly switch statement that does all the math inline, we use functional dispatch. We look up the operator string, and it returns a first-class function that knows exactly how to manipulate the stack. This is a game changer, because if you want to add a new multiply or divide operator tomorrow, you just add one new function to your map. You don't have to touch your core interpreter loop at all.
Section 2, the engine room interface-based AST.
But what happens when a simple stack isn't enough? What happens when your language needs nested logic and really complex hierarchies? That's when we leave the stack behind and move to an abstract syntax tree, or AST. In an AST, every single piece of our language is a node in a tree, all defined by a common interface. Let's say we have an operation sum node. When our interpreter calls read on that sum node, it doesn't just do the math right then and there. It recursively calls read on its left child and its right child. And those children might be simple numbers, or they might be entirely separate sum or subtract nodes. This brilliantly illustrates the composite design pattern embedded directly inside the interpreter pattern. It's recursive tree evaluation at its finest.
Let's actually contrast these two approaches side by side. On the one hand, we have our stack approach. It's flat, it's sequential, and it uses functional dispatch to just crunch through tokens one by one. On the other hand, we have the AST approach. It acts like a hierarchical factory, building a complex, recursive tree of nodes.
The stack evaluates as it reads, whereas the AST builds a whole map of the program first, and then evaluates the tree. To help you choose the right tool for the job, let's look at the exact trade-offs. The stack is incredibly simple, very fast to implement, and great for basic linear logic. But it's really hard to extend for complex grammars. The AST is highly extensible, type-safe, and incredibly composable. The catch? It is significantly more complex to write and generates way more memory allocations as it builds out that tree of nodes. It's your classic spectrum of complexity versus power.
Section 3. The Pragmatist's Guide. Philosophy of Language Design. Okay, let's step out of the engine room for a second. Why do we even bother designing new languages in the first place? And when should you actually deploy this pattern in your own systems? There are three main reasons. First, to simplify repetitive operations. Think about how SQL saves you from writing raw database search code over and over. Second, to empower non-programmer users. Just like our musician from earlier needing sheet music, your domain experts need a DSL to express business logic without writing a single line of Go code. And third, system interoperability. Things like protocol buffers act as a completely neutral language that multiple different systems can easily understand.
But listen, here's the absolute core tension of language design. The power of your language is inversely proportional to its simplicity. It is so tempting to make your DSL do everything under the sun. Don't do it. Build only the absolute simplest grammar needed to solve the problem. Why? Because every single feature you add to a language is a maintenance commitment you are making forever.
When you keep things simple, the interpreter pattern absolutely thrives. Here are the deployment scenarios where you should use it. Building rules engines where your business logic becomes actionable data. Query builders that generate database calls. Parsing chatbot commands to figure out what a user actually wants. And configuration DSLs. Just think about how Terraform uses HCL to manage complex infrastructure. These are all phenomenal use cases.
Section 4. Constraints. What could go wrong?
Now, I have to warn you, it's not all smooth sailing. Building your own interpreter opens up some very specific, severe pitfalls. You really need to pay close attention to these danger zones. For instance, if you try to build an interpreter for a truly complex grammar without using a dedicated parser generator, you're going to have a bad time. If you put an interpreter on a performance-critical hot path, your app will literally crawl, because interpretation is basically always slower than compiled code. You also face some severe runtime dangers. What if a user passes a division by zero? What if the input is totally malformed? What if your AST triggers unbounded recursion and just completely blows up the stack? And finally, strong coupling. Once your users start writing rules in your DSL, you can almost never introduce a breaking grammar change without ruining their day.
But hey, do not let those danger zones stop you. Let's end on this thought. Build your own expression evaluator. Start with just sum and sub, and you'll understand every rules engine you ever encounter. I really challenge you to go write a simple stack-based evaluator in Go tonight. Take the mystery of how SQL or regex works and turn it into true mastery. Thanks for hanging out with me for this explainer, and happy coding.